Good afternoon. Good afternoon and welcome to the AAAI 2019 Robert Engelmore Memorial Lecture. This particular award is named after Robert Engelmore, who was the first editor of AI magazine. The award is given every year to someone who is an outstanding scholar in AI, who has a record of sustained service to both AAAI and to the AI community, and who, in addition, has a sustained record of having impact that goes beyond the AI research community to the real world in terms of applications or social impact. This year's award winner has another distinction that Bob Engelmore also had, and that is he's a good fellow. So will you please join me in welcoming Milind Tambe.
Thank you. It's really a great honor to receive this award, and it's really a great honor to be here among all our friends. So thank you for this invitation. So with the tremendous progress in AI and multi-agent systems, it is now important to direct these advances towards societal benefits. I'll focus on three areas: public safety and security, conservation, and public health. Viewing these societal problems as multi-agent systems, there's a key research challenge that can be seen to cut across the three areas. How to optimize our limited intervention resources when interacting with other agents in these domains. And I'll focus on the use of computational game theory as an approach to address these challenges. With respect to public safety and security, we have a large number of targets to protect, but limited security resources. How to schedule or plan or allocate these resources, taking into account a watchful adversary. We've contributed a new model called Stackelberg Security Games and contributed new algorithms that have been used by security agencies in the United States and internationally. With respect to conservation, we have large conservation areas to protect, limited ranger resources. We've contributed a new model called Green Security Games. A concrete example is work we've been doing in Uganda. Using past poaching incidents, we are able to predict where poachers may set traps or snares. And for the past several years, we've been able to remove a large number of snares and even get poachers arrested. The model is being extended towards combating illegal fishing and illegal logging. With respect to public health, we have a limited number of social worker resources. Concrete example is work we've been doing in homeless shelters in Los Angeles. Taking into account the social networks of homeless youth, we've shown that our influence maximization algorithms, based on the idea of games against nature, are far more effective in spreading HIV information compared to traditional approaches. We are now extending this work to combat tuberculosis, obesity, and other public health challenges. All of this work is only possible because of the partnerships with governmental and non-governmental organizations. To that end, we have really patrolled with the US Coast Guard on their boats in New York. Our students have spent time in homeless shelters, working with homeless shelter officials. This immersion is important to collect the right kind of data, on the basis of which our predictive algorithms, machine learning, can predict high versus low risk cases. This is then fed into a prescriptive algorithm which plans game theoretic interventions. What's also very important to us, though, beyond that, is field testing and deploying our work. This is important not only because we are extremely interested in social impact, but because this is how we can discover new research challenges by understanding the weaknesses of our models and algorithms. So in the rest of the presentation, I'm going to go through the three areas mentioned. I'll start with public safety and security, because this is early part of our work. I see a lot of new faces who have not seen this. So I'll spend about 10 to 12 minutes on this part of the work. It lays the foundation for the rest of the presentation. All of the work I'll discuss has been published in conferences like AMAS, AAAI, and ICHKI. This is where you'll find lots of simulation results. But in this talk, I'll focus on real-world evaluation. There are also these series of books. If you buy these edited books, then from the royalties, I can take my students out to a very nice dinner. So I hope you will buy them. I also wanted to thank my PhD students and postdocs. And so to that end, I'll have their pictures in the top right-hand corner of the slides on which their work will be shown. So let's start with public safety and security. Clearly, this is a global challenge. Events of 9/11 were clearly devastating for all of us. I've grown up in the city of Mumbai in India, and it has suffered a series of attacks. For example, on 11th of July 2006, bombs went off on the trains in Mumbai. My mother was traveling on one of the trains. Fortunately, luckily, she got off the train before the bombs went off. But this raised the importance of public safety and security in my mind. So when the chief of airport police at LAX approached us to improve security at the LAX airport in Los Angeles, we were all ears. His concern was somebody driving a suicide truck into one of the terminals has happened in Glasgow in 2007. There's 8 inbound roads into the airport, 8 terminals, and so the question is, where and when do you schedule checkpoints? Where and when do you do canine patrols? The challenge for us was whether we could use game theory for security resource optimization. Could we convince the scientific advisory committees that game theory was the right approach? Could we convince our AI reviewers that this was the right approach, given that leaders in the field were suggesting that game theory was not useful? Could we convince sergeants on the ground that game theory was the right approach? Well, that's what we decided to do. We proposed a new model called Stackelberg Security Games, which I'm going to illustrate using a simple 2x2 game. So we have one defender resource. If the defender is always at terminal 1, an adversary conducting surveillance will attack terminal 2. The adversary gets a positive reward of 1. The defender gets a negative reward, -1. In fact, any deterministic strategy the adversary could defeat. If the police were to use a randomized strategy, mixed strategy, 60% of the time they're at terminal 1, 40% at terminal 2, then an adversary conducting surveillance will only know that the police are at terminal 1, 60%, terminal 2, 40%, but what they'll do tomorrow remains unpredictable. These kinds of games are called Stackelberg games because the defender commits first to a randomized strategy, and then the adversary responds. These are security games that are played on targets where payoffs are based on whether targets are covered or not. We are interested in optimizing the use of limited security resources. We are not guaranteeing 100% security because in the real world, there is no such thing. We are increasing the cost and uncertainty to an adversary in coming up with a plan of attack. So this is how the armor system was built for LAX Airport. We start with a game matrix that's fed into a mixed integer program, which provides a mixed defender strategy. For example, the probability there's a canine patrol at 8 a.m. at terminals 2, 5, and 6 is 0.17. Probability there's a canine patrol at 8 a.m. at terminals 3, 5, and 7 is 0.33. And then we sample from this distribution to generate an actual schedule. For example, at 8 a.m. send team 1 to terminal 2, team 3 to terminal 5, team 5 to terminal 6. At 9 a.m., do something different. And this is an actual schedule that the police officers can then execute. Here's how the mixed integer program is written. We are trying to maximize defender expected utility. Rij refers to the reward of the defender if the defender takes a strategy I and the adversary takes a strategy J. Xi is the probability with which the defender takes a strategy I. For example, X1 is the probability that there's a dog on terminal 1 and a dog on terminal 2. X2 is the probability there's a dog on terminal 2 and a dog on terminal 3. For every single combination of defender resources to targets, we have a probability variable. Qj models the adversary's response. We model the fact that the adversary conducts surveillance of our mixed strategy and then provides the best response. Where do the payoffs come from? In this case, the threat was somebody driving a suicide truck into one of the terminals. The loss to the defender then would be the loss of human lives that would occur if such an attack were successful. We had from the airport detailed numbers on how many people are present at different times of the day at different terminals, and that's how we could generate the payoffs. For all of the domains I'll discuss, we have numbers on potential loss of human lives, potential economic consequences, and that's the basis on which we generate our payoffs. Now, of course, these numbers are not perfect. We need to be able to handle uncertainty. We have spent enormous amounts of time dealing with this uncertainty. In this talk, given limited time, I'm not going to go into that. But with all of this framework in place, Armor was operational at the LAX airport. It's the first such application of computational game theory for operational security. There was news media, local TV, that started covering the use of armor and weapons that were captured at the checkpoints. So you can see in January of 2009, all these weapons that were captured at the checkpoints. The LAX police department was clearly happy with this, and so was someone at the City Hall, because we were very honored to receive commendations from the city of Los Angeles. That's me and my students. So up to that point, we had been fortunate to have received Best Paper awards, but this was a really great honor from the city. Errol Southers even went to Congress to talk about our work, and so this is from his appearance in a US Congress committee hearing.
LAX is safer today than it was 18 months ago. A team of research led by Dr. Milen Tombe worked with our department to develop armor. This software randomizes our vehicle checkpoints along airport access roads and the deployment of our explosives detection canine teams throughout the airport.
This led to news media coverage. For example, Newsweek saying armor throws a digital cloak of invisibility. So at the next Amos conference, my colleagues were asking me if we were working on a cloaking device at USC. But this led to an invitation from the Federal Air Marshals. This is from our visit to the Freedom Center, home of the Federal Air Marshals. Right at the entrance there is a memorial to 9/11 victims, rubble from the Pentagon, rubble from the World Trade Center, pieces of the planes that crashed into the World Trade Center, really motivating us that whatever these Federal Air Marshals ask us to do, we should really execute. So their challenge was how to assign air marshals to flights. There's thousands of flights, and this problem becomes very difficult to scale up. So here's why the problem becomes such a difficult problem to solve. We have 1,000 flights here, and you could imagine assigning air marshals to flights 123, 124, 135, and along the columns here are all different ways an adversary could attack flight 1, flight 2, up to flight 1,000. There's 10 to the power 41 different rows here, because there's 10 to the power 41 different ways in which we could assign air marshals to flights, which means that there's 10 to the power 41 different xi variables in this mixed integer program, which means that this program cannot run. It cannot run, but if we could make it run, what we would find is that most of these xi variables are 0. The support set size is small, and we can even show that for security games of T targets, optimal solutions of support set size T+1 always exist. So if we could somehow magically know in advance which of these xi variables are going to be set to 0 and remove them from the game matrix, we would be left with a much smaller game matrix, which if we solve, we get the exact same solution as the larger game matrix. And that's the insight on the basis of which we built a new exact algorithm for scale-up. The basic idea here is incremental strategy generation. Is the first such algorithm for these Stackelberg security games. We start with a master problem with a small number of pure strategies. There's a slave problem using LP duality theory, gives us the next best pure strategy to add. And we iterate in this fashion until we converge to a global optimal, except now the global optimal has only 1,000 defender strategies rather than the 10 to the power 41. So this is how we built IRIS, which is this program that's used by the Federal Air Marshals to assign air marshals to flights. If you've been a US air carrier, United, Delta, American, etc., whether there was an air marshal or not on your flight may have been decided by this program. In 2012, we were very honored to have our work again mentioned in a United States Congressional Committee hearing, and a certificate of appreciation from the Federal Air Marshals. This got us an introduction to the US Coast Guard, and for them we built this system called Protect to generate patrols in ports like Boston and Los Angeles and New York. Protect, like armor, is an acronym. This is to tell you that we've spent enormous amounts of time coming up with good acronyms. One of the big novelties in Protect was generating patrols around the Staten Island ferry, which is a moving target. These are our algorithms that completely changed how the Coast Guard generated these patrols. I'm going to illustrate how we generated these patrols using transition graphs. For simplicity, I'm going to use a discrete space-time graph. So here there's 3 locations, A, B, and C, and 3 time points, 5, 10, and 15 minutes. The dashed lines show all the different ways in which boats can move in this graph. So for example, the ferry can go from C to B to A, shown by the green line. A patrol boat is shown here by the red line. And in fact, the patrol boat can take many of the red and brown lines. So you have exponential n to the power t routes, n being the number of locations, t being the total number of time points. So you have n to the power t variables in your optimization problem. Very difficult to scale up. We show that if we use marginal probabilities over segments of routes, as shown by the thick red and brown arrows here, then we are left with n squared multiplied by t variables rather than the exponential n to the power t. And we show that these marginals can enable scale up with no solution quality loss. So with this, we were able to generate patrols for the Coast Guard. We were thrilled that they appreciated the work, and we received commendations from the commandant of the Coast Guard in a surprise ceremony in their Atlantic area headquarters, and honored that our work was again mentioned in United States Congress in a committee hearing.
We're working with the University of Southern California to utilize game theory as a way of optimizing and scheduling our patrol. It makes it harder for somebody to anticipate where the patrols will be.
So we have continued this work forward, generating patrols to catch fare evaders, people traveling without tickets on trains, and we are thrilled to see many security game applications around the world. The ones in Africa relate to protecting wildlife. I'll come to that in a minute. But before that, let me talk about real-world evaluation. We've spent significant amounts of effort evaluating security games in the field to show that they're superior in optimizing the use of limited security resources when compared to traditional approaches, whether it's human schedulers or simple random. So I'm not going to be able to show you all the data we have, but just to give you a few examples, this is patrols in the port of Boston before Protect was deployed. Along the x-axis are different days of the week, and along the y-axis is how frequently a particular target was visited. For example, the green line at the top shows how frequently on day 1 that target was visited, on day 2, on day 3, and so forth. There's very few patrols on day 2. So this was a good day to attack the port of Boston. All these lines crisscross, meaning sometimes a target is more important, next day it becomes less important, third day it becomes more important, but targets actually don't change their value from day to day. If you look at patrols after Protect, the more important targets are visited more, the less important targets are visited less. On any given day where the patrol boat will go will remain unpredictable, but on the whole, the more important targets are visited more. If you look at it from the perspective of defender expected utility, there's a 350% improvement from before to after Protect was deployed. The Air Marshals did a 6-month study comparing human schedulers against game theoretic schedulers, and the conclusion was the Irish program was superior. There's a Government Accountability Office report from the US government that talks about the weaknesses of human schedulers. We also did a study of 90 police officers. We scheduled them on trains in Los Angeles, once using human schedulers, once using our game theoretic schedulers. And we had neutral observers observing these patrols at different stations, grading them on 12 questions. Their conclusion was that the game theoretic patrols were superior. So the human beings who had done the scheduling had spent 2 days to come up with these schedules, but in the end, their patrols were worse. We also sent patrollers on trains in Los Angeles for 21 days under identical conditions, sometimes using our game theoretic patrols, sometimes using a baseline approach to catch people traveling without tickets on trains. Their conclusion that the game theoretic patrols led to 60% more captures of people traveling without tickets compared to a baseline approach. At the checkpoints at the Los Angeles airport, there's 5-fold increase in numbers of captures of weapons and drugs and so forth. Again, all of this is evidence that security games are superior in optimizing the use of limited resources compared to traditional approaches. Today, we've worked with the TSA to improve processing at checkpoints for the TSA. This is not deployed yet, and also cybersecurity. So let me now move on to the second topic, which is wildlife conservation. This is work done with Dr. Andy Plumtree in conservation biology. So before we begin, let's think about what it is that we are fighting for. This is Murchison Falls National Park in Uganda. There's wonderful wildlife here, but there's threats to the wildlife, snares or traps that are used to maim and kill animals. In fact, thousands of these snares used to kill animals annually. To optimize the use of limited ranger resources, we provided a new model called Green Security Games. So if you think about the Queen Elizabeth National Park, for example, we can divide up this park into 1 kilometer by 1 kilometer grid squares, where each grid square becomes a target. Now we can run our mixed integer program just like before to generate patrols, but there is a difference. The adversary here is not this fully strategic adversary, but instead we have multiple boundedly rational poachers. So they're not going to provide this rational best response, but instead we're going to learn the adversary bounded rational response at each grid location I based on the past poaching data. So given the range of patrol frequency in that grid cell and the features of the cell, we are trying to learn the probability of finding a snare in that grid cell. So we're trying to learn this function GI, and then we can optimize our patrols having learned this function GI. So attention now shifts to learning this function GI at each grid cell. We have 12 years of poaching data from Uganda, and we are trying to learn this probability of finding a snare. We have features like distances to roads and rivers, range of patrol frequency. The one difficulty, though, is that when the rangers walk and tell us that there is no snare found in a particular grid cell, it could just be that had they walked just a little bit more, they could have found a snare. So the negative instances here are not something we can find reliable. So to handle this uncertainty in negative instances, we create this ensemble model where we create multiple filtered data sets. So for example, in one filtered data set, all negative instances where the patrollers have walked less than 1 kilometer, we remove all those negative instances because we don't trust them, and then create a classifier. In a second filtered data set, all negative instances where the patrollers have walked less than 2 kilometers and said they didn't find a snare are removed because we don't trust that report. So we don't learn another classifier. And in this way, we learn a whole bunch of classifiers, and then at test time, we create an ensemble so that when a new instance comes in and a patroller has walked, say 1 kilometer, only 2 of these classifiers are used. If they've walked 2 kilometers, 3 of these classifiers are used, and so on. So we ran a lot of simulations in the lab using test data. We are able to show that our best model performs better than other baseline approaches. But this was clearly not adequate for our partners, Uganda Wildlife Authority and Wildlife Conservation Society. They wanted to see demonstrations in the field. So we created, so in a real world deployment test, we selected these 2 9 square kilometer patrol areas where there were infrequent patrols, and these were not previous hotspots. So we recommended to them to patrol on these green dots, and you can see that they don't overlap with the red dots, which is where poaching incidents had been reported in the past. So we are not just asking them to go back to where they had patrolled before and found crime. This was done 1 month before a conference deadline. So if we are able to find snares, then we'll be able to write a paper. If there's no snares found, there'll be no paper to write. Patrollers went out for a month, and every day they would send us an email as to what happened. Initially, nothing, and then a poached elephant with its tusks cut off. So the machine learning system was asking us to go in the right direction, but we were too late to save this elephant. Then good news, a whole elephant snare roll was found. So poachers were active in this area. They were killing elephants, but before they could kill the next set of elephants, we were able to remove a large number of snares and thus potentially save lives of elephants. And then a whole antelope snare roll and so forth. Our paper reports our hit rate versus the base hit rate, but this started to generate confidence that this model is really going to work in the field. Now, one concern here is that this is Uganda. If you go to a national park, go to a place where there haven't been many patrols, you're just going to find snares. To address this criticism, we did a 6-month trial, a 6-month test in 2 separate national parks in Uganda, Queen Elizabeth National Park and Murchison Falls. We selected 24 areas and predicted some of them to be high risk and some to be low risk. And for 6 months, patrollers were out patrolling these areas. At the end of 6 months, for example, where we predicted in Queen Elizabeth high-risk areas, in fact, many more snares were found than areas where we predicted low risk. In Murchison Falls, we had made high, medium, and low-risk predictions, and in fact, where we predicted high risk, many more snares were found than in the medium risk than in the low risk. So this has really generated some excitement that these models are really going to work in a large number of national parks. But it is my belief that we have to continue to test these and continue to improve our algorithms. So today we are conducting tests in Cambodia in the Sri Pak Wildlife Sanctuary. This is the site where tigers will be reintroduced in the Southeast Asia after their wholesale slaughter. So we sent them our predictions in December of 2018, and the first day of January of 2019, I got the best email of a new year that I could get, all these photographs of snares that were found based on our predictions. So we had sent them these predictions of high risk and low risk areas, and they found, where they found the snares in fact matched our predictions. High risk had more snares compared to medium and so forth. But what was also important is that there were 521 snares that were found in this 1 month of our test, compared to 101 snares per month in all of 2018. So this is clearly very exciting, not only to us, but our partners, World Wildlife Fund. And I got this email from Rohit Singh, head of WWF in Cambodia. Milind, I'm super excited with the results. Let's get going on other countries too this year. So this is what we plan to do. So far I've talked to you about this pipeline that goes from data to decisions, where we are trying to learn predictions from ground truth data. Now I want to talk to you about incorporating real-time information from drones. And this is work done jointly with an NGO called Air Shepherd. They fly drones in South Africa and Botswana, and at nighttime take infrared video, which is sent to a van where there's a human being sitting, watching the video, trying to detect poachers. You can see it can be quite difficult to detect poachers from infrared video late at night, and so forth. So taking advantage of recent progress in computer vision using convolutional neural networks, we built a system called Spot to automatically detect poachers and animals on these videos. And this system has been delivered and is being tested in Botswana at this point. So here's how it's supposed to work. Air Shepherd will fly their drones. Spot will detect poachers at night in the vans, and a human being is supposed to call a ranger to say, hey, if there's poachers, go intercept them. But of course, rangers may only arrive with a small probability, let's say year 0.3, because we don't have as many rangers around. So poachers may not be stopped in many of these instances. So what to do in this case? What our collaborators, the Air Shepherd people do, is do deceptive signaling. So when there is no ranger, they'll turn on the light late at night and fly the plane towards the poachers to indicate to them that rangers are on the way. And in fact, the poachers are seen to run away if that happens. But of course, if you always do this, where you turn on the light and fly towards the poachers when there are no rangers, they're going to figure this out, that this is an empty threat. So we need to be strategic in our deceptive signaling. This strategic signaling, deceptive signaling, is part of the PhD work of my former student, Haifeng Xu. So we've generated these Stackelberg security games with optimal deceptive signaling. The idea is to use the informational advantage that the defender has. The defender knows not only the mixed strategy, but the pure strategy of whether the ranger is actually there. So for example, and I'm going to use this very simple example, we have a ranger available with a probability of 0.3. When the drone flies overhead, it not only knows this probability, but it also knows whether the ranger is actually there or not. When the ranger is present, it will honestly signal to the poacher that a ranger is actually present. So in this case, we are honestly telling them the ranger's on the way, run away. When there is no ranger and the drone flies overhead, it knows that there is no ranger, and it happens with a probability of 0.7. In some of these instances, it is still going to signal to the poachers that there is a ranger on the way when there is none. So the basic idea here is this deception is done in just enough frequency that it is still in the poacher's best interest to believe in this signal and run away, even though they know that 50% of the time they are being lied to. So, and in the remaining instances, of course, the drone will honestly signal that there's no ranger on the way when there is no ranger. So we are being strategic in our deceptive signaling, and it turns out that such strategic signaling reduces the complexity of our equilibrium computation. So with all the progress that's been made in terms of predicting where poachers may set snares, in terms of spotting and detecting poachers, and the work that we've been doing in order to improve deceptive signaling and so forth, there's now significant interest in taking this software to many other parts of the world. And to that end, we have been partnering with SMART. This is a collaboration of different wildlife conservation agencies, WWF, WCS, and many others. They are active in 600 national parks around the globe. Their software is used in order to track animals and poachers and so forth. And collaborating with them and Microsoft's AI for Earth, we are now integrating our software with SMART so that our own software will be available to protect wildlife in 600 national parks around the globe. So this is happening right now. We hope this will start generating data this fall. And so if any of you are interested in collaborating with us, we welcome collaboration because there will be a lot of data that will be available. And we are extending these models towards protecting forests and fisheries as well. So let me come to the third part of this presentation, which is public health. And this is work done jointly with Professor Eric Rice of social work. So the challenge here is preventing HIV amongst homeless youth in Los Angeles. We have 6,000 homeless youth who sleep on our streets every night. The rates of HIV among these youth are 10 times the rates of the normal housed population. So we don't have enough social workers, and so the shelters, homeless shelters then, run these peer leader campaigns. So they'll try and find peer leaders whom they can educate about HIV, and the peer leaders will then go and inform others in the community about HIV. We are talking here about real social networks and not Facebook and so on. So this is the problem of influence maximization. We have given a social network graph G. We are choosing K peer leaders to maximize the expected number of influence nodes. The assumption here is that information spreads with this independent cascade model. So when we inform a node A, a homeless youth A, about HIV testing, there's a probability of 0.4 that adjacent homeless youth B will be informed about HIV testing. Immersion in this domain, though, showed us that we can't exactly know these probabilities. So to model the uncertainty, we can sample this uncertainty from, sample the propagation probability from some distribution. And to further model this uncertainty, we say that the mean of this distribution lies within some interval. And now we have this challenge of influence maximization under uncertainty. To solve this problem, we can cast this as a game where the algorithm, our algorithm, is trying to choose a policy, choose K peer leaders in order to spread information about HIV, and nature is trying to choose parameter values for these distributions in order to make an algorithm perform as worse as possible. So the payoffs of this game is this form of regret, which is a ratio of the performance of our algorithm to the optimal. So the influencer is trying to choose a policy, choose K peer leaders, and nature is trying to choose parameter values to make our algorithm perform as worse as possible. Of course, there's a large number of choices for our influencer, which peer leaders to select, and large number of choices for nature in terms of which parameter values to select. So solving these games becomes difficult, scale up is difficult. If you go back to the earlier section of the talk, you know we talked about incremental strategy generation. So here we use a similar idea, except it's now this double oracle where there is an influencer's oracle that will incrementally add strategies for the influencer. And there's nature's oracle that will add strategies for nature. So we incrementally build up this game until we converge. We can show that even though nature is sampling from a continuous set of values, we converge to an equilibrium with approximation guarantees. So this allows us to handle this uncertainty. But there is a second form of uncertainty that we also have to deal with. we have capacity limits. So even though we may want to educate, say, 12 peer leaders, we can't invite all 12. The homeless shelter has capacity limits. We can only bring in, say, 4 peer leaders at a time. So we invite these 4 peer leaders to come in, but one of the youth on the way may get arrested and may send a substitute. Someone else may have to run away. So the people who show up may be quite different from the people you actually invited. So in the next time step, when you bring in the next 4 youth, you have to take into account who showed up in the first time step. So this is planning under uncertainty and partial observability. So the policies here are really POMDP policies. And this is the work, so we need to solve these POMDPs very quickly. And of course, this is difficult. This is the work of my former PhD student, Amulya Yadav, in his PhD thesis. He shows how these POMDPs can be solved by exploiting partitions, existing sub-communities within the homeless youth. So the combined system of this game theoretic model and this POMDPs is called Healer. And the question then is, how will Healer perform in the field? So we tested 2 versions of Healer. We recruited about 170 youth. So 60 under the Healer, another 60 for another version of Healer, and then about 60 for degree centrality, which is the more traditional approach, which is bring in the most popular youth. We selected 12 peer leaders in each of these cases, and our social work colleagues then educated these youth about HIV. They went out into the community, and the question is, who is able to spread more information about HIV? The results were that our Healer algorithms were far more effective in spreading HIV information compared to the traditional degree centrality, bring in the most popular youth. So amongst the non-peer leaders, the people that we did not bring in, 75% of those got informed about HIV compared to the traditional approach where only 25% of those non-peer leaders got informed. So our algorithms were far more effective in spreading information, but did they actually lead to change in behavior? So if you look at what fraction of those who got informed actually started testing for HIV, we see that among those who got informed by Healer, 30 to 40% of those started testing for HIV. But with those who were informed with the traditional approach, no one started testing for HIV. And this is in part because there's a smaller number of people who got informed about HIV in the first place. There is a Journal of Social Work Research article that came out recently that has many more details about these results. So we are interested now in taking these results out to many other cities. But one bottleneck here is data collection, because the way this algorithm is set up, the first step is to collect information about the entire social network. So this is a tedious effort. You can imagine a social worker sitting in a homeless shelter trying to do some surveys, trying to do field observations, and even with uncertainty, try and map out the social network of the youth before our algorithms start rolling. So the question is, can we reduce this burden? So to that end, the question is, could we sample something like, say, 18 to 20% of the network, a small fraction, and then choose peer leaders? In our AAAI 2018 and AMAS 18 papers, we show that we can do this. We can sample from the largest communities and then select peer leaders, and this works well in simulation. Okay, so works well in simulation, how well would it work in practice? So again, we recruited 60 homeless youth in one of the homeless shelters, chose 12 peer leaders, but these were selected from sampling of 20% of the network, as I mentioned. How well does it perform in the real world? Again, we see that even though we had sampled only 18% of the network and then selected peer leaders, the sampling algorithm was just as effective as the original Healer algorithm, which knew the whole network in terms of spread of HIV information. And furthermore, in terms of HIV testing, the sampling approach led to as much HIV testing as with knowing the entire network. So we are very optimistic about what these results show. This means that potentially we can take these techniques out from Los Angeles, out to San Francisco, New York, and other cities. And our partners are also very excited by these results.
Beautiful way to kind of like marry this tech world with this social service world, like, and how we can kind of go deeper and impact young people and elevate them.
If this group became a really big thing, it could really help out a lot of youth.
We are now completing a study of 900 homeless youth in 3 different homeless shelters, and towards the end of this year, we should expect to see these results come out. So let me now talk about a public health challenge in a different part of the world, which is preventing tuberculosis in India. Tuberculosis is a global menace, but in India it kills 500,000 people a year, and 3 million people are infected every year. So we focus on patients in low-resource communities where non-adherence to TB treatment is a major challenge. So they have to take 6 months of treatment, so basically they have to take pills every day for 6 months, and people drop off because it's very difficult to keep doing it. It's not only bad for the patient, but it also means that you get drug-resistant bacteria. So this is not really a good thing. People should adhere to treatment. So more recently, in many countries, there are these digital adherence tracking technologies. So for example, here, what we're showing is a blister pack. You open the pill, and it shows a phone number, and patients are supposed to call that phone number so that people who are tracking this can know that this patient has been taking their medicine because they've been calling every day. So we will know when somebody has stopped taking pills and they haven't called for a few days, then we know this person is dropping off of their treatment, and we can try and intervene on them. But that may be too late. Can we, from their calling pattern, predict adherence and then intervene on them before they actually start missing doses of their medicine? So this is work that we've been doing jointly with EverWealth Health Solutions and Microsoft Research India. EverWealth is a social enterprise. And this is a picture from our visit to EverWealth's offices in Bangalore. So EverWealth collaborates on software that serves millions of TB patients in India and other countries. And so here's the kind of dashboard that we see. We see here patients where, for example, patient ID 6214 has called for 3 days, then didn't call on day 4, day 5 and 6 they called, day 7 didn't call. Can we predict what's going to happen next week so that we can intervene on the patients that may drop off of treatment? So for example, if this is what's going to happen, we should be able to predict and intervene on patient 6214 before they drop off. So we have data of 15,000 patients, 1.5 million calls from the state of Maharashtra in India with collaboration from EverWell. And so using random forests or LSTMs, we are trying to predict high-risk patients. So for example, consider these 4 patients. The first one did not call on the first day, but called on the remaining 4 days. Second one called on the first 2 days, did not call on the 3rd day, called on the 4th day, did not call on the 5th day, and so forth. Could we predict which of these are high-risk patients based on their call patterns so that we can then intervene on the high-risk patients? So if we could predict number 2 and number 4 are the high-risk patients and go there and say, you have to take your medicine next week, that would save us because we don't have enough social workers to go to every single patient. And then based on these predictions, we can prescribe, we can do interventions based on all our intervention constraints and then send social workers out in the field. Now, one of the challenges here is to make sure we are robust in our high-risk predictions. Patients, for example, may not be able to call on the weekend, so there is essentially some kind of noise in the data. And so we can cast this again as a game against nature, where we are trying to predict high-risk patients, where nature is trying to perturb the samples to reduce prediction accuracy. Solving this game then gives us a mixed strategy, randomization over multiple predictors. And with this, we can show that our model is able to achieve 35% improvement over EverWell's baseline. The baseline is a rule-based system that predicts high-risk patients, and we are able to improve this prediction accuracy by 35% in terms of true positives and then reduce the false positive rate. So this is already an improvement, but we can do better. So this is the idea of decision-focused learning. So up to now, I've talked about this data to decision pipeline where we are doing stage-by-stage reasoning. So in the machine learning phase, in the prediction phase, we are trying to get it as accurate as possible by itself. However, in our AAAI 2019 paper, we show that if the constraints of the decision module, intervention constraints, are taken into account in the loss function of the prediction module, then that would improve predictions just the right way in order to get our intervention module to be more effective. So decision-focused learning is seen to improve the TB interventions. So if you look at it in terms of overall accuracy, the stage-by-stage approach leads to higher machine learning accuracy in terms of predicting who are the high-risk patients. But if you do decision-focused learning, what we see is that interventions improve. This is because this decision-focused learning is improving accuracy where it matters on those patients which we can intervene on, because improving accuracy of patients we can't intervene on doesn't really help us. If you're interested in this topic, then I recommend going to Brian Wilder's talk tomorrow, Wednesday at 11:30 a.m. So this whole progress has been very exciting for our collaborators. For example, Bill Thies, who's the co-founder of EverWealth Health Solutions, points out that this work has a lot of potential to save lives. And hopefully I'll be able to report back when this potential has been realized. So I've talked to you about 2 projects on public health. And so I'm going to talk to you very briefly about a couple more. So for example, one project in Antelope Valley, north of Los Angeles, is looking at childhood obesity, where obesity leads to risks such as diabetes, stroke, and heart disease. So we want to do early intervention with mothers. This is work done jointly with our School of Medicine. And essentially the idea is use social networks and social influence to get them to change their diet and activity. So there's competitive influences in this network in terms of health, positive and negative, and we show in our AMAS 2018 paper how to add and remove edges in this network in order to influence behaviors. We have done this work in simulation, and the idea now is to try this work out in practice in the field. Another project is looking at suicide prevention. The challenge here is to train gatekeepers who can keep an eye out in their social network on people with suicidal tendencies. The problem, of course, is that not all gatekeepers will be actively engaged, and so we can cast this as a game against nature, where we are trying to choose gatekeepers while nature is trying to make sure that some of them do not participate, and then solving this game allows us to choose the right gatekeepers to have robustness in our approach. So with this work in HIV prevention, in terms of the work that's going on in Antelope Valley for childhood obesity prevention, suicide prevention, work in substance abuse prevention, we are doing all these projects in the city and county of Los Angeles. When the mayor of Los Angeles, Eric Garcetti, came to USC recently and talked about the moral and humanitarian crisis that we are facing with the large numbers of homeless in our city, large numbers of homeless youth, I'm very grateful that with AI research, as an Angelino, that I can contribute back and we can contribute back to our city. On the other side of the world, as a Mumbaiker, I was very honored to sign a memorandum of understanding with the government of Maharashtra in the capital city of Mumbai, in the presence of the chief minister of the state, to use artificial intelligence for societal benefit in Mumbai, in Maharashtra, and rest of India. So I've already talked to you about tuberculosis prevention. There are many other projects that we're pursuing, how to optimize the resources for TB prevention, how to allocate them more efficiently. Our students are visiting TB primary health care clinics, challenges related to how to spread information about health that's pursued using social networks. So anybody who's interested in combating these challenges of tuberculosis in Mumbai, Maharashtra, or HIV prevention in Los Angeles, we are very open to collaborations. So I'll end here by pointing out that we are focused on directing multi-agent systems research towards social good. We focused on 3 areas: public safety and security, conservation, and public health. I pointed out a shared multi-agent research challenge, which is to optimize limited intervention resources when interacting with other agents, and a solution approach based on computational game theory. Research contributions, by engaging and executing things in the field, we see new kinds of models arise. For example, Stackelberg security games and green security games, and new algorithms for incremental strategy generation and use of marginals and double oracles. As I look towards the future, I see tremendous potential for AI in improving society and fighting social injustice. And to that end, it's vital to bring AI to those who have not benefited from it, particularly in the global south, and to embrace interdisciplinary research, particularly with social work and conservation. And when we are working on AI for societal benefit, it is important to step out of the lab and into the field, not only because we care deeply about the societal impact, but because this is a way in which we can find weaknesses of our models and algorithms to generate new and important research challenges. So to end, I'll thank many of my collaborators in this work. I have been blessed with many, many collaborators in this field, but I'm going to list here those with whom I've written at least 5 papers in the last 10 years. And this includes Sarit Kraus, Vince Konitzer, Eugene Vorobeichik, Andy Plumtree, and at USC, Eric Rice, Bisra Dilkina, Phoebe Villanos, and Fernando Ordonez. And I also wanted to thank Barbara Gross, who has been a tremendous mentor from Harvard for many years. I also want to thank all the different partners for really inspiring us. At this point in time in particular, very important to thank the men and women of the Coast Guard, the TSA, for all the different work that they're doing, for the rangers on the front lines who are trying to protect wildlife, sometimes at the risk of their own lives, and for social workers, whether they're in Los Angeles or Mumbai, trying to help the marginalized community. So thank you very much. Thank you for attending.
Time for questions?
Hi. Thank you very much for your beautiful examples. Before this presentation, I knew of negative examples like people coming up with a black box method for predicting crime that gets adopted by decision makers, this kind of ideas. So how could you manage to convince people to try your solution, be it with your math? Like, was it only through simulation, or did you manage?
No, this is a very important question of how to convince people to use our approaches. And it usually starts out with a meeting where the people, policymakers are, the people sitting like this saying they don't want to use our solutions. But with the immersion and demonstration of the software and so forth, and then trials in the field, over time, they can see the benefit of using AI techniques, and that's how we've been able to convince them in order to use our approaches.
Thanks a lot for the very inspiring talk and all the work that you've done in this area. So I'm wondering, you mentioned a few times the pipeline going from data collection to deployment in the field, prediction, optimization, deployment. And I imagine you also touched on evaluation in the field, and I imagine there are other aspects to that as well, of identifying the problem and transferring algorithms, insights from one problem to another, one domain to another. So I'm wondering if you can comment on any lessons learned, challenges that do exist in this pipeline, failure cases that you've come across, anything that someone else who's in this room trying to replicate what you've done could find value in knowing about.
Thank you for that question. I mean, there are many lessons here, and a lot of this really requires immersion in the field, and evaluation takes a lot of time. So, for example, you have to wait for 6 months, 2 years sometimes for the trials to complete, and so there are a lot of lessons here. One of the big ones, of course, is being able to be understanding of the fact that we're working with people who may not be as familiar with our techniques, and therefore we may need to be very patient in terms of explaining, just as they need to be very patient in terms of explaining what they are doing. There's just so many different lessons, but very quickly, when the first time we implemented these models at the LAX airport, for example, the question that they raised was, this model is, there's some bug in the code because this is not random. So you say, okay, why is this not random? That's because, well, it's generating checkpoints at the same place at the same time 3 days in a row, and random means it has to change every day. So this is sort of at a very basic level. But there are very interesting research challenges that come out of actually implementing things in the field. And so I'll give another example, and this is the reason why it is important to try things out in the field. So when we were generating patrols in Malaysia, for example, we would send them patrol routes, and they would, on Skype calls, come back and tell us that, this is not working. Somehow there's something wrong. The shortest distance between 2 points in Malaysia is not a straight line. And so the only way to try to understand what was going on was to actually go there and patrol in the field. And then suddenly you realize that if you just ask people to walk in a straight line in a forest, they have to go up and down. They lose a lot of energy. That doesn't work. So you really have to give them patrol routes that follow ridge lines and riverbeds. And there's a hidden street map that allows them to patrol without losing much energy. And so these are the kinds of things. But there's so much to discuss and such an important question that it requires a longer discussion. Thank you for your question.
Thank you very much.
Hi, so thank you so much for your talk. I think your work on especially 99 dots Everwell, that's like really high impact work. But as an Indian and as somebody interested in the healthcare space, one problem I've seen is adoption of technology, especially by patients and doctors. And this is more evident in the unorganized healthcare sector in India, in clinics and dispensaries and so on. And part of it is because of there's a bit of inertia and maybe going away from, going towards technology and away from something like paper-based prescriptions and all of that stuff. So basically technology adoption seems to be a problem here. So, and especially predictive tools, like there's research done on predictive prescriptions and all of that. So what do you think about this gap that's been coming in technology adoption in these areas?
Again, a wonderful question, and it requires a lot of discussion. But notice that here we are already working with this Everwell software platform, and they have already deployed with millions of patients. And so we were already working with deployed software platform, and we are improving their prediction technology, which they are already using in terms of trying to detect high-risk patients. So I agree that there's going to be difficulties in adoption. There's going to be this, we don't need your solution first, but we believe that over time, as they see the benefits of this approach, that our approach will get adopted, just as we've seen in all of these other examples.
Yeah, I mean, in many cases, you see that the work's obviously very great, but sometimes, especially from people, less well-off areas, they would rather, trust a doctor over something like a solution given by a computer or an algorithm.
Right. So here, they're already. What I'm saying is that we are already working with a well-established NGO in the field, and so we are not, adding a completely new dimension of technology. So as a result, I believe that the overhead here is much less because the hard work of actually being in the field and getting the software to work has already been done.
Yeah, thank you so much.
Hi, I really liked your talk, and it's great to see how AI is being used to make the world better. My question is related about online social networks, and basically I see that you guys spend a lot of time trying to build the social network from observation. So I was wondering if you could comment why not using online social networks to try to bootstrap these relationships between the youth, for instance.
So the work we are doing here is in low-resource communities where the homeless youth, for example, do not have access to computers or cell phones. They have some, earlier they used to have something called an Obama phone where they had some limited time and they would use that to call their parents or loved ones. And so there's really no access available to them from where we could track their online social networks. And so therefore, we have to rely on field observations in order to understand who's interacting with whom in a, in a face-to-face setting. So that's why for our work, a lot of the effort has gone into sampling from small populations and so on. And we believe that in many marginalized communities, that this is the kind of work that would need to get applied. But I would love to see if there are opportunities to combine it with online networks as well.
Thank
Sorry
you.
that we will have to stop here, but please join me in thanking Milind Tambe for a very inspiring talk. So the next. The next event is going to be the Oxford-style debate on the future of AI. We're going to give you a couple of minutes to get out of the room if you want to do something else, or to come into the room if you think this sounds like awesome time, which it's going to be. And we'll let the panelists all come up and join me up here as well. this, and really we know it's after 5 p.m. here in Hawaii. Because we're very close to the international dateline, it's almost surely very much later in whatever time zone you came here from. So we know everyone is in a relaxed frame of mind, and we want to have fun doing this. We've got an amazing panel of debaters who I'll introduce you to in a moment, and they have all agreed to take on really extreme points of view that may be more extreme than the ones that they actually hold themselves. So I hope that you all have a good time. I hope the panelists have a good time, and let's begin. And to show what a fun thing this is, I'm putting on a fun Hawaiian lei to signal our spirit of fun. So here to begin, let's get started by framing the debate. So the proposition that the panel will be considering today is the following: the AI community today should continue to focus mostly on machine learning methods. I'm going to begin by introducing our panel. I'm going to give a really high-level biographies of each panelist because our panel truly is so esteemed that if I was to give any reasonable sort of biography for each of them, I would take up too much time from the debate. So I'm going to do them in alphabetical order, which actually I think corresponds exactly to the order in which they're sitting here, as it happens. They really did well for me. To your right here, Oren Etzioni is the Chief Executive Officer of the Allen Institute for Artificial Intelligence, previously a professor of computer science at the University of Washington and a venture capitalist in Madrona. His research is focused on basic problems in the study of intelligence, machine reading, machine learning, and web search, or at least that's what Wikipedia says, and if it's not true, he should edit Wikipedia. His most cited paper is titled Extracting Product Features and Opinions from Reviews. Michael Littman is a professor of computer science at Brown University. He works mainly in reinforcement.
I just took off my glasses, but I did it with flair.
He has a reputation as a funny guy, but really that was pretty good, even without saying a word. He works mainly in reinforcement learning and also has important contributions in machine learning, game theory, computer networking, POMDP solving, and computer solving of analogy problems. His most cited paper is titled Reinforcement Learning: A Survey. Jennifer Neville is an associate professor of computer science and statistics at Purdue University. Her research focuses on developing data mining and machine learning techniques for complex relational and network domains, including social, information, and physical networks. Her most cited article is a chapter in the book Introduction to Statistical Relational Learning on Relational Dependency Networks. And last but not least, Peter Stone is a professor of computer science at the University of Texas at Austin. His research contributions are mainly in the areas of machine learning, autonomous agents and multi-agent systems, robotics, and e-commerce. His most cited paper is titled Multi-Agent Systems: A Survey from a Machine Learning Perspective. So let's have a round of applause for our esteemed panel here. So you've all had a chance to review the proposition on the screen while we've been talking, or actually maybe you haven't because it's showing our boring faces. If we could have the slide up again for a moment. There we go. The proposition here is the AI community today should continue to focus mostly on machine learning methods. So in the tradition of an Oxford-style debate, we'd like to begin by asking all of you to vote. We'll do it unscientifically by show of hands, and scientifically, but with whatever biases are introduced through this methodology, by voting on Twitter. So you can search for the hashtag AAAI19debate, which will show you the poll that you can vote in. It's only going to be open for a few more minutes because we don't want you to be swayed by the debate. And then later on in the debate, we'll open up another version of this poll that you can vote in again. But first, by show of hands, how many of you are in favor of the proposition? All right, you guys have your work cut out for you. And how many of you are opposed to the proposition? Wow. My goodness, no way of calling that was going to happen.
And we're done.
So it turns out that in order to win the debate, the against side has to sway more votes than the for side. So they're going to have a tough time with so few people available to be swayed. We're going to begin by hearing from somebody on the for side giving an opening statement. And I guess that's you?
Okay, thanks, Kevin. Can you hear me okay if I talk like this? Yes? Okay, so I guess I expected there to be more hands for the machine learning side in the audience, but maybe everybody was too busy submitting their ICML papers last week to make it to Hawaii to support us here. So Peter and I are on the for side, and what we wanted to do was start off by, I'll try back here. We wanted to start off by talking about the goals of AI research, just to set the framework for what we're going to say. So our view, which of course the other side can disagree, is that the goal of AI research is to really understand the nature and limitations of computational intelligence. And maybe we'll learn where to put the microphone. And
Time's up.
We also aim to create robust autonomous agents that can behave rationally and intelligently. So for what I wanted to start with to make my first point was to go back a little bit and talk about the history of AI. So for those younger researchers in the audience, the field of AI was really created in 1956 at a summer conference formed by John McCarthy and Marvin Minsky and Claude Shannon. And there was a lot of excitement and interest in developing algorithms that could behave intelligently at that point. Obviously, we've had more than 50 years of research in this field since then. But I want to also point out the story that is perhaps told apocryphally among students, that in 1966, Seymour Papert told his grad students to solve computer vision in a summer project. So in a couple months over the summer, to just create an algorithm that would be able to take an image, a percept of an image, and be able to automatically identify what was in the image just as we see. And the reason he thought it was something that would be solvable over the summer is that he said, unlike many other AI problems, it was tractable and easy to encode. And so, of course, this is one of the things at the beginning of the field of AI where people really overpromised as to what AI was capable of at that time, and that really led to what was called the AI winter in the 70s, where US Congress was very unhappy with all the money that they had funded in the field of AI and the lack of progress that had been made. And so really at that point, people thought that we wouldn't be able to have algorithms that were capable of expert level chess playing, that we wouldn't be able to do simple tasks like face recognition or common sense reasoning. But as I am a child of the statistical machine learning wave that came through in the late 80s and 90s, really things started to turn around at that time. One of the examples was when IBM started to use statistical language models for machine translation. And really, at that point, what people started to do is use very large data sets, labeled data sets, to start to learn how to train these models. And the improvements in machine translation led to products like Siri and Google Translate, which of course are some of the breakthroughs that we've had in NLP. Also later than that, 1995, Jerry Tesaro had used reinforcement learning to create the first backgammon playing program that was able to achieve champion level game playing in backgammon, and notably learned opening strategies that humans had not used so far. In 2006, we had the Netflix competition where Netflix offered $1 million to the machine learning community to just have at their problem of predicting movie ratings from their users. And what they wanted to do was have someone develop a machine learning technique that could reduce their prediction error by up to 10%. And the winning team, which was a combination of people from AT&T Labs and some other researchers in Austria and Quebec, used an ensemble of more than 500 models with gradient-boosted decision trees in order to solve this problem. And really, this led to a resurgence of interest in recommender systems. And of course, companies like Amazon and Netflix have made a lot of money from that. Netflix says that 75% of what people watch today is from some sort of recommendation that they've learned. Then, of course, we had in 2012 Hinton applied his deep learning algorithms to ImageNet, and they had the first system that was able to break the 75% accuracy on image recognition tasks, which of course led to a whole host of advantages and breakthroughs in vision. Of course, I want to remind people that in 1966, that they thought it would take 2 months. But it took deep learning and another 50 years to solve that. And then in 2016, of course, we had Google's AlphaGo be able to beat championship Go player Lee Sedol using a combination of reinforcement learning and deep learning.
15 seconds.
Okay, so all of those breakthroughs that I pointed to in terms of the history of AI were all due to machine learning. So, therefore, I would argue that we need to keep focusing on machine learning because that is where we are making all our progress.
Thanks very much. Let's hear something from the... All right, as nice as it is to applaud when somebody says something clever, we're going to have way too much applause throughout the whole debate if we keep doing that. So let's keep our applause until the end. But let's go to the first. So whichever of these guys is going to be the one to speak, there'll be no applause greeting him in response to his comments.
Thank you, Kevin. I'm Oren Etzioni, and Kevin asked me to be provocative, which, if you know me, is like waving a red cloth in front of a bull. I'm happy to oblige, but I should remind you that the views expressed don't represent the views of the Allen Institute of AI, my colleagues, or even my own. Really, any resemblance between what I'm about to say and what I actually believe is purely accidental. The last 5 years or so have seen 3 major populist movements globally. First, the populist movement in the United States, which landed the Donald in the White House, at least temporarily. 2, the populist movement in the UK, which led to the disaster called Brexit. And 3, I submit to you that we're in the midst of a 3rd populist movement towards machine learning. You might ask,
Come on, I made it less than a minute, guys.
I need the extra time. You might ask, what's wrong with ML? ML is a great field. We get good results. We publish papers. We get funding. We're hip and sexy again, at least some of us. But I worry. I worry about an AI winter. If you have any doubts that an AI winter may be coming, just look outside. I mean, we came all the way to Hawaii, and today was a total disaster. Look, populist movements are all fine at first. We're listening to the people want to publish, they get 10% gains on various tasks using variants of LSTMs, CNN, ABC, HBO. But what happens when these populist movements get stronger and more entrenched? They spin out of control. On the surface, there may seem to be little similarity between these populist movements and the situation in AI. But let's have a closer look. Let's look at the key figures in these movements. The Trump movement had Roger Stone, a guy who imitates Richard Nixon, quotes from The Godfather, and dresses like Hannibal Lecter. Stone was arrested last week by FBI agents who were not even getting paid because of the partial government shutdown. They volunteered to arrest him. The machine learning movement has Peter Stone. Roger Stone, Peter Stone. Coincidence?
I don't think so.
In case you didn't hear that, coincidence?
I don't think so.
The ML populist movement is plotting a shift away from any symbolic methods. It's nothing short of Brexit, a hard Brexit, a no-deal Brexit. Jennifer Neville's most recent paper is entitled The Indian Buffet Hawks Process to Model Evolving Latent Influences. In other words, Brexit. Coincidence?
I don't think so.
They're trying to build a wall between ML and AI. Walls work, they say. Mexico will pay for it, they say. But we know better. Okay, let's get a little bit more serious, and let's dispense with a few obvious points. ML has been incredibly successful, as Jennifer pointed out. Deep learning has exceeded our wildest expectations. The heart of the ML success story is supervised learning with doses of semi-supervised and reinforcement learning. But it's essential that we define ML for the purposes of this discussion. Our worthy adversaries, confronted by our cogent arguments and various jokes, may attempt to squiggle, squirm, wriggle away, and redefine ML in various speculative ways. But that, of course, makes any serious discussion impossible. Don't be fooled. ML is ML is ML. We have to nail it down as what ML really is, which is supervised learning with a cherry on top. In reality, ML is very limited. Humans, many of them here, set the target concept, decide what the data is, label the data, iterate through the experiments, choose the neural network architecture, choose how to regularize. We all know that it takes blood, sweat, and tears to get any ML system to work. Human blood, sweat, and tears. So-called machine learning is 99% manual human engineering. Now, if you want to build AI savants, like the Netflix fries that Jennifer mentioned, or for speech recognition, face recognition, object detection, there's nothing better. But the ML populist movement is claiming a lot more. Take AlphaGo, for example. In AlphaGo, ML got the top billing. But what about Monte Carlo stochastic search? How many positions did AlphaGo have to consider before the ML could do its thing? You don't hear much about that. Take AlphaZero. It learned superhuman intelligence. Just a few more seconds, please, because of the applause and the laughter and
that was most of your 15 seconds.
Please. I'm almost done. Take AlphaZero.
Thanks so much, Oren. Okay, so now over to the other side.
I'll continue later.
Thanks for those great remarks about Brexit and to some extent AI. Now we'll turn to our second debater, Peter Stone.
We knew exactly what he was going to say and prepared this statement perfectly for that. I want to remind you that what you're asked to judge is not how deep our voice is or how funny we are or whether machine learning is the only solution in AI. The question is, should the AI community continue to focus mostly on machine learning methods? We can take a big tent view of AI. We agree that there's many different methods that require attention and that can be useful. But we should continue the focus on machine learning in this community for now for two reasons. Number one, because it's currently our weakest link in terms of knowledge. And number two, because we have the critical mass as a community to make rapid progress now. In a few years, inevitably what we learn will reinvigorate the other still essential areas of artificial intelligence that are being kept alive by relatively smaller communities today. Focusing now mostly on machine learning is healthy for our field and should continue. The history of AI, Jen gave the machine learning perspective and some of the successes. But it's true, there have been many successes over the years. Decades of artificial intelligence were devoted to understanding how to do symbolic reasoning if we could eventually solve the perception problem. As Jen pointed out, it was thought that that would be the easy part. It then became recognized that it would be impossible to solve the perception problem with certainty. So at least a decade was devoted to developing methods to reason about uncertainty with the assumption that we could solve perception probabilistically. We're now in a phase of focused attention on understanding the degree to which machine learning can be used to recognize objects and decide what actions to take, and to understand the degree of uncertainty in these learned models. This knowledge will feed into the previous focus areas. This is very healthy and should continue. So let me be clear. I'm not taking a position on whether machine learning is more important than any other area of AI, as our esteemed opponents are trying to paint us into saying. I agree that we ultimately need a broad set of approaches within the field, and I agree that we need some focus on all of them at all times. But regardless on your position on the question of whether machine learning is more or less important, now is the moment for machine learning in our field. Most of our community has been focusing. 60% of the papers in this conference were submitted in machine learning, vision, and natural language processing. And this should continue for at least some more time. What will this focus provide? If we do focus on machine learning, we may be able to answer some of the questions once and for all. With a few more years of focus, we may be able to sufficiently explore neural network architectures such that that's no longer a core research area or community of our community. 10 years from now, I hope I'm not still reading papers about how to stack convolutional layers, recursive connections, and LSTMs. Let's get it over with now and outsource the fine-tuning of tools to industrial tool developers. We can also leverage the current energy to make significant progress on some of the hardest, still underexplored areas of machine learning. For example, learning how to act using reinforcement learning algorithms. There have been a lot of exciting results in the area, but there's still huge questions remaining pertaining to how to scale it up using transfer learning, one-shot learning, human interaction, common sense reasoning combined with reinforcement learning. We have a lot of energy in our field. Why should we throw that away? So my summary is that we should be continuing the focus on machine learning for now because it's our weakest link. We don't yet know the limitations in terms of knowledge and because we have the critical mass as a community. In a few years, as I said, we'll be able to reinvigorate our focus on symbolic reasoning informed by our progress in machine learning, in probabilistic reasoning and reasoning under uncertainty informed by our progress in machine learning. These areas should be kept alive. The statement is not that all of our focus, but that we should continue to focus mainly on machine learning methods. Focusing now mostly on machine learning is healthy for our field and should continue.
Thanks very much, Peter. What are we doing? No! Oh, you're breaking my heart.
It's good at the end.
Oh, okay. All right, so now to the man who made you laugh by taking off his glasses. We're going to see whether the substance hilarity chasm on both sides of me here will continue.
Whose side are you on?
I'm just trying to keep it interesting.
I see. All right, well, let me start off by saying that I have nothing against ML. I mean, after all, it's my initials. But that being said, Peter would have us keep the rest of AI, all the rest of AI, alive in small, dedicated communities. And I think that really misses the point and is historically problematic. One of the things that I'm really worried about is we've got 60% of the papers in machine learning-related disciplines at the moment. But what about the change from year to year? It wasn't 60% last year. It was, I don't know, maybe it was 30% last year. And next year it'll be 120%. Okay, it's possible I need to do a little more machine learning. But that being said, this is a trend that could actually squeeze out the rest of the really important ideas if we don't decelerate now and find a way of getting this back under control. And it's so disappointing to have Peter and Jen arguing the other side here. You know, what happened to you guys? Your theses were so good. I mean, Jen worked on relational learning, which is about machine learning, but in the context of really interesting and important structures, and not just sort of we're going to just throw as many neurons in a pile as we can. And Peter's work was on hierarchical learning, which again, it's learning, but it's tamed learning. It's learning in the context of a structure that's actually going to get you something beyond just statistical relationships. So it's a little sad. I was going to say that we had the easier side to argue, but it turned out that was exactly true. I mean, everybody's kind of already on our side. Partly because I think there's a lot of ways attacking the problems of creating intelligence, and machine learning is just one of them. And so our side is right if it's anything else. Of course, on the other hand, machine learning has been doing some remarkable things and has the attention of the crowd. But I think that one of the things that machine learning is doing to be so successful is redefining problems so that they're really well suited to machine learning methods. And I had an interesting thing happen a couple weeks ago where I was on a phone call with Peter Norvig. Do people know Peter Norvig, co-author of the Big AI textbook along with Stuart Russell, who I don't think he's here. And I just keep imagining that I see him everywhere because if you've watched him give talks, he's almost always wearing a Hawaiian shirt. How could he have missed this? Like, this is his element. This is his time to shine and show us what we've been doing wrong all these years. But anyway, that's beside the point, and I'm using up my time. in the conversation, I was making a case for more structured kinds of problems and being able to solve harder problems in robotics by using more of the structure and not just machine learning approaches. And I said that, we don't see people solving problems like I worked on a number of years ago, crossword puzzle solving, right? So think of crossword puzzle solving as a deep learning problem. It would be kind of a big mess. And so I said this to Peter Norvig, and he said, well, one of your collaborators on that work is working for me at Google now doing deep learning, so QED. And I'm like, no, he's not doing deep learning for crossword puzzles. He's doing deep learning for like analogies and these other sorts of surfacey problems. So I feel like he really missed the point there. To me, the machine learning systems are really attacking a different part of cognition than kind of more classical AI attacks. I think of it as being like System 1 and System 2, if you know that sort of Kahneman Tversky breakdown, where System 1 is doing, machine learning is doing System 1 stuff really nicely, this kind of gut level reaction to things. But people who are actually weak in System 2 in reflection and thought, they really don't seem like smart people to us. And there's an absence of structure and consistency. And it's sloppy, and it's not the kind of thinking on which you can build complex structures, or intelligence for that matter. Things just fall apart. There's no long-term coherence. And I wanted to give an example of this because, puns. So the pun generation is something that's been attacked by both classical AI methods and machine learning. If you don't know about punning riddles, here's an example of a punning riddle that I found on a website, but could have written myself. What do you call a green cow in a field? Invisible. Right, that was really funny, so I'm glad you all agree. Okay, so a machine learning system, a kind of classical deep learning system, was trained up on tons and tons of these punning riddles, and after the training was done, this is what it was able to come up with. First of all, did you get the invisible one? I feel like maybe you didn't get it. You got it, you just didn't like it. Is that clear? Okay, all right, good. At least you got it. That was the important part. The machine learning, thanks. The machine learning system that actually was trained on these punning riddles produced the following winner. What do you call a short sense of humor? A charming saucer. Right, it just smacks of what you get from these deep learning systems. Like, it sounds like a joke, and you think it's got the surface properties of a joke, but all the internal consistency, all the meaning, all the depth, if I will, is missing. There's nothing deep in the deep learning. It's very surfacey. Here's a GoFi example, just so that I can leave you with that. A system was built using kind of classical AI knowledge-based kinds of methods, and it came up with, what do you call a murderer that has fiber? A serial killer. And that worked better than the human one, right? So we're done here. Don't clap, because he'll be
All right,
mad.
let's clap for everybody. Why not? Get it out of your system. But not just for Michael.
That's fair.
All right, so now we're going to transition to the free-for-all phase here. I'll ask a few questions to prod things along if need be. I'll start by inviting each debater in turn to react to one thing that somebody else said that they particularly felt deserved a reaction, or if they don't think anything on the other side deserved a reaction, something they previously talked about with Peter Norvig that they think deserves a reaction. So whoever would like to go first.
I'll start. I wanted to just pick up on a couple of points that Peter Stone made. First of all, Peter Stone and I definitely agree. Just like Roger Stone, he's got a perception problem. Peter would have us ignore that in the 80s, there were 9,000 people at AAAI in the 80s. Think how many there would be today. But his divide and conquer type of arguments have really contributed a lot to the balkanization of AI. The biggest point I want to make is he talked about we don't want to throw ML away. Of course we don't want to throw it away. We just want to note that it's a tool, it's not a panacea, and it's one of the tools in our toolbox.
Wow, I didn't even have to cut you off. Okay, who'd like to go next?
So thank you, Oren, for reiterating my point exactly. It is a tool. It is one of the tools in the toolbox. It's one that we know the least about so far, and the one that we should be putting our focus on now because it's the least developed of all the important tools. I'd like to respond to a couple of points. One that Michael made, that I'm asking to have small dedicated communities keep other threads alive. In fact, that's exactly what happened during the time that Oren is referring to, and recently when neural networks were a small, just kept alive community, and now it's blossomed. These other communities, we need to keep them alive, but they'll have their light of their time in the sun now, in the future, but not now. We need to continue our focus now on machine learning. Michael talked about our theses.
Yeah, one reaction.
Oh, this is all one.
Nice try.
Oh, come on.
I'll cede my time to Peter because I'm interested to see what's going to happen.
The others are...
All right, go for it.
So, you talked about our theses. I will point out that Michael's thesis was also quite good. It was about algorithms for sequential decision making using machine learning. Yes. He was working on machine learning throughout. I would also like to respond, but not really counter some of the other arguments of our opponents. Yes, Peter Norvig should be here. I agree. Yes. Yes, Trump built a wall.
It's nice that we found
I
some
agree.
common ground.
And yes, my name is Stone. I also agree. But none of those are the question under debate. The question under debate is that the AI community today should continue to focus mostly on machine learning methods, and that's what we should be doing.
All right, nicely done. I think it's your turn.
Yeah, I kind of gave up.
Okay, great. So I guess I wanted to respond to two things, so I'm going to group them into one comment, just like Peter did. So when Michael said that he was disappointed in Peter and I for originally being machine learning people that worked on complex structure problems and still being machine learning people that worked on complex structure problems, I would say one of the problems is then I applied deep learning to my tasks, and deep learning worked better. So, but I guess I would argue that so first of all, when we say machine learning, we do not just mean deep learning. All of these things that I think you're arguing are important to AI are actually what we're including in our umbrella. I think the main point that I would make is that as a field in AI, all of the problems that we want to tackle are basically intractable problems. If the problem is tractable, we let somebody else solve it, right? So as a community, we start off the bat asking if something is intractable, and really we've gone to larger and larger intractable problems over time, and I think it's machine learning that's helped us search through those spaces. So when Oren said that nobody really gave the Monte Carlo search in AlphaGo its due, it's really that the machine learning was helping that search work through the space that was so intractable that we couldn't possibly search over it. So I will stop at that point.
All right, so now I have a question, I guess, that I'll ask just to get things going, which I'll direct to the no side here. It's been mentioned at this table both by the program chairs at the beginning of the day and again by the for side that a majority of the papers submitted to AAAI indeed are working in the machine learning space. On the other hand, we see something like 2/3 of this room, according to the Twitter poll, voting against this proposition. You guys are arguing against the proposition. Some of you, like Michael Littman, use the word machine learning all over your own webpage and in the title of your thesis. What do you guys think is going on here? What's with the focus on machine learning, but the notion that we shouldn't focus on machine learning?
I think it's very simple. If you're thinking in the short term, again, publishing your next paper, machine learning is great. It's a paper publishing methodology. But yesterday yesterday in the roadmap session, the question was raised, how do we build a general theory of intelligence? This is a great question. It's one of the most profound questions of all of science. It's a question that brought me, and I would conjecture even, pro-Brexit Peter Stone to the field. And we're going to need a lot more than ML to answer it. Are we really going to answer the most profound questions in all of science by multiplying matrices and doing gradient descent? Come on.
So when can we moderate our views? This is very uncomfortable for me.
Not yet.
I should mention that in the closing statements after the free-for-all section, which has another 5 or so minutes to go, the panelists will then be allowed to reflect on positive things that the other side said and moderate their views and stop playing the roles they've been assigned. But
That's
for
when
now,
you can
Michael,
admit you were wrong, Michael.
Let's hear you talk about how terrible machine learning is and why you shouldn't work on it.
So,
We never said that.
clear, right. Well, and also to be clear, the moderator said that machine learning was in the title of my thesis, and it's not. It's just in the title of basically all of my papers. So, you're wrong.
Yeah, so here I have your last 5 papers. Learning from demonstration, compression and apprenticeship learning, deep reinforcement learning, model-based reinforcement learning, multi-step model-based reinforcement learning.
Right, but I try to do this to get papers published. No, that's just wrong. How could you have backed me into that corner?
We've all been there, Michael. We
Oh,
understand.
I'm so sorry. All right, so in spite of that, I would venture to claim that my work is crap. No, stop. Why are you guys doing this to me? This is horrible. All right, so that it's very important to do the machine learning in the context of structures, right? That we can't just do end-to-end, just let all the numbers just work themselves out, because we learn absolutely nothing from that. And so, so there.
I just like to clarify, right, the proposition, and this is an important point, right, is about it being mostly machine learning. So we're not in any way anti-machine learning. You know, I did my thesis with Tom Mitchell. We're talking about, again, and you can argue about mostly, right? But clearly the other side, and you can see it in the arguments, is much leaning, you know, in the 80, 90, 95%. But let's not bargain over the price. Let's think about the fundamental questions. One point that Michael made to me before the debate is about cognitive architecture. Think about it this way. What's more complex, intelligence or your Chrome browser? Your Chrome browser's got 7 million lines of code. Are we really going to learn automatically 7 million lines of code? No, we have to build an architecture. We have to have some innate knowledge. We have to do a lot more than just machine learning. So mostly machine learning ain't gonna cut it, Peter. Sorry. Thank you.
Okay, now you can moderate your views, Oren.
Yeah, let me give the foresight here a chance to react if they like.
So again, I don't think we're disagreeing about in the larger sense.
Oh, we're disagreeing, Peter.
No, we're not. Yes, general theory of intelligence is what the AI community should be focusing on. As Jen started out with, we as a community, our big questions to understand the nature and limits of computational intelligence, to enable the creation of robust autonomous agents. And yes, in the long run, we take a very big tent view. All areas of artificial intelligence are important, but, where's my butt?
You're sitting on it.
To solve to take this big tent view, we do need logic, we do need probabilistic reasoning, and we need machine learning. But we already know as a community, to a good first approximation, what to do once we have the symbols. We don't need to reinvent that now. We know how to reason with uncertainty. We don't need to reinvent that now. What we don't know is what degree of uncertainty we can capture these symbols with when perceiving the real world, and how to act. That's what we need, not for forever, not for all the past, not for all the future, but now. That's what this statement is about, that the AI community should be focusing now on going to as far as we can with machine learning, understanding the limits, and then bringing it back into the fold with all these other very important areas that will help us answer these big questions that Oren raises.
Right. Last word to you.
I guess I would like to go back to John McCarthy's statement at the Dartmouth Summer Conference that he said every aspect of learning or other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. So I just want to point out that the first thing he mentions of intelligence is learning, and so our focus on machine learning methods is really at the core of AI as it was described to begin with.
Jen, are you really arguing for machine learning based on the statement that John McCarthy was right? Really?
I was wondering about that too. All right, well, now is the phase that will come as a great relief to some, if not all, of our debaters, where we'll invite them to make closing statements which will either allow them to retrench the positions that they've expressed throughout the debate, or if they prefer, to distance themselves from some of the extreme things they've said and to reflect on the other side of the debate. We'll do this in the opposite order that we made the opening remarks. So we'll begin with what appears to be our most eager person to change his view, a one-man debate in himself, Michael Littman.
That's a good way to describe it. It does feel like inside my head there's always these arguments going on. I'm like, and you know what? You're right too. No, wait, no, you're right. So no, this was really interesting, and kind of I signed up to be on this side when the statement was slightly different. It was a stronger statement that I felt really good about. But this sort of mostly thing, I'm not sure I buy actually sort of Peter's story about. I mean, it was a clever use of the words, but this sort of idea that, well, mostly for now. But later, of course, we're going to not have mostly, and that seems a little cheaty. Like, you know, I guess it doesn't say indefinitely, but it sort of, I don't know, reads that way to me.
It says continue.
Continue indefinitely to focus mostly on machine learning methods.
This is the most emphatic debate you've made for your assigned side.
I know. Well, so one of the things that really struck me though is Oren said, well, we can't understand big questions about like science and what things really mean in the world with ReLU units, multiplying it. But the experience that I've had this year has actually been quite different. I've been working with some scientists at my university, and they're super excited about deep learning. They really want to do deep learning, and partly it's not because they think that they're going to get a deeper understanding, but because most of the equations that they've worked out are so complicated that actually solving them to say what's going to happen in a physical system is intractable. And so what they want to use a lot of deep learning stuff for is leaping over that complicated computation and just getting to something like the right answer. Which I thought it was really interesting that I would think they would be the biggest holdouts of all, but in fact they're also now on the deep learning bandwagon. Other sort of concluding, how long do I get?
You got another minute.
Another minute. Yeah, and I mean, I really do worry about this issue about the surfacey structure that you get with a lot of these deep learning systems, where they just don't have internal consistency. You listen to the machine-generated music, and it's just not music. It just sounds like music until you listen to it for just a minute, and then you realize it's just nonsense. And I'm very worried about this sort of idea that we can redefine the problems so that what we're actually thinking about is can we generate better nonsense? And that seems like not progress to me. But I do think that ultimately machine learning is completely integrated with the picture that we need to be generating. We can't throw away the machine learning piece. We need to figure out how do we do machine learning in a way that supports deeper, maybe more symbolic reasoning. And I'm not sure that it's the case that we can just say, oh, well, we know how to do symbolic reasoning, so once we get to that point, boom, we're done. In fact, I think we have to think about how symbolic reasoning needs to change to support what we've learned from the machine learning studies of using this low-level information to come up with better inferences.
You're a contradiction. You fervently wanted to adopt the pro-ML position, and then when the fetters were taken off, you made cogent arguments for your assigned side. I don't know what to think. Okay, Peter.
So when we decided on this question, and Kevin told us to start preparing a mere 5 hours ago, my knee-jerk reaction was the same as yours. I felt like I could have argued either side. In fact, probably that the AI community should not continue to focus mostly on machine learning methods. That was my initial reaction. But in the days and weeks that Jen and I have spent forming our arguments, and to prepare for the completely predictable statements that our opponents would make, trying to argue the other side. It's become clear to me, in fact, that this statement is true. And like you're about to do, I changed my mind towards the statement that the AI community should continue to focus mostly on machine learning methods for the reasons that I've laid out. That we at our current state of knowledge within the field, it is our weakest link. We know much more about the other important aspects of artificial intelligence, that we now have the critical mass as a community to make rapid progress in machine learning like we never have before, and that by doing that now, we will be able to put all the pieces together towards the very big and important questions that have been facing our field for many years and will continue to face our field. Now is the moment for machine learning.
Cogent arguments as well. Doesn't take away from it at all that the reason we changed the question 5 hours ago was that you came up with this question and argued that we should all adopt it. Oren.
So at the end, you should make. Oh, never mind. Go ahead.
Kevin, let's not get personal here. That's my job. I'd like to first of all point out that my worthy adversaries in no way addressed my comments about Brexit and Donald Trump. But again, more seriously, since our impartial moderator, accused our side of somehow lacking in substance, clearly we are in the midst of one of the most amazing paradigm shifts in, again, all of science, certainly computer science. Machine learning is incredible. The only point, and I think it's a point that all of us would agree with, is that we need to go beyond building classifiers, beyond slightly incrementally better machine learning methods, to think about the deep issues that we face in AI, which require synthesis of machine learning with other techniques. I'm talking about interpretability. I'm talking about stability and robustness. I'm talking about the use of common sense to avoid brittleness. I'm talking about fairness in machine learning. I'm talking about choosing what to learn in the first place. Cognitive architecture. As Michael pointed out before he got cold feet, the problems that we thought about, for example, cognitive architecture, were problems that Newell and Simon studied in the 80s. We haven't solved these problems. We've just gravitated away from them. So we do need to solve these problems with machine learning, but we can't just do machine learning, which is what, unfortunately, all too many of us are doing. Thank you.
All right, thanks. And now to our final panelist, arguing what seems from your vote to be the underdog side. Let's see if you can change some minds.
Okay, I was going to express my views on the other side.
Or you can express your, that's true, you're also allowed to do that, or you could just join them.
So I guess I wanted to say that when we got together as a panel to discuss this earlier today, we decided that we're all very practical people who want to solve real problems in AI, and so it was going to be hard for us to decide which side to argue for and really make a cogent, coherent argument only for that side. So I think that we really all, in our complex approach to solving problems, include machine learning methods with a host of other techniques that come from other aspects of AI. So we're focused on knowledge representation, search, complex objectives, planning and decision-making, reasoning in open worlds where we have to be able to generalize to novel tasks and situations that we haven't seen before. And I don't think that as a community we should focus solely on function approximation as the only solution to these complex problems. So although function approximation might account for 80% of the solution, there is a lot else that goes into tackling these problems. And I do agree with Oren's point that he made somewhere in his Brexit rant, that that as a community, the ML community tends to focus on formulating tasks that are uniquely designed that their methods are going to work well. And so I think the unique strength of the AI community is that we really focus on the tasks that need to be solved, and instead of finding tasks that we already can solve or are very close to where we can solve them. And so in that sense, I guess I'm arguing a little bit for the other side. So let me just wrap up, though, to address the Brexit and Trump comments that Oren made. And I would say the big takeaway that we should all remember from that, those events, is that we needed better machine learning methods for political forecasting and persuasion in order to avoid those events. So thank you.
All right. All right, now, what a great panel, what a tremendous job they did of blending fun and strong argumentation, helping us all to think about a topic that I think we all really deeply care about as a field. Nothing remains except for us to hear from you. So first of all, the Twitter vote has been open for about 10 minutes. That's what I was doing on my phone. So you're welcome to go onto Twitter and vote a second time, and we can see if your vote's changed. But let's do a show of hands. So first of all, raise your hand if your vote changed, if you're about to vote in a different way than you voted at the beginning of this debate. See, doesn't that show the power of reasoned argument to change minds, to really reach people, literally as many as a dozen people? Fantastic. Okay, so how many of you are for the proposition that the AI community today should continue to focus mostly on ML methods? Raise your hands. And how many of you are against the proposition? All right. I think I'm going to say that's too close to call. No, look at the Twitter response. But I invite you to come up to the microphones if you have a question for the panel or just something either amusing or cogent that you feel was overlooked by our panelists. They're kind of midway down the two rows.
Isn't quite my question, but I saw it on Twitter and wanted to repeat it. Why are all the panelists machine learning scientists? That's biased, just like many models learned by machine learning. There you go.
I think for the best place to see, to think about intelligence, to look at human intelligence and human brain. And I think we have amazing power to find patterns and immediately react and make sense out of it. And we plan and we have strategic things, and we use our experience and knowledge over the period of time. So what has happened is that in the growth of machine learning and deep learning, all the focus is on finding the patterns and looking at the data that is there, and some limited way of characterizing the data, particularly in the classification problem. On the other hand, so many of the tasks are much more complex than that. We have our human perceptions, we have our cognitive abilities, and so on and so forth. And what we have not done enough of is to integrate. Now, the structured aspect of it that has been done is reasonably limited in the past in terms of what you model in the structure. Our brain probably represents the things in far more complicated and nuanced way than our limited data structures, limited hierarchical modeling, and so on and so forth. So I think the great challenge is to figuring out how do you model the knowledge appropriately, and how do you infuse that knowledge with the learning processes to make it much more powerful, to combine the bottom-up thing that we have done recently well with the top-down things and make for the real intelligent processing.
So thank you for your comment. And now that you've all put in your last votes and failed to change your minds at all, I want to say that I appreciate this comment very much. That I believe in this community, this is a really important community, and I'm actually very encouraged that that people are saying that we do need to focus on integration, taking many different methods and put them together. That is not, we should recognize that's not the case in all communities in AI right now. There are sort of growing movements where, you know, there is a debate whether all of intelligence should be done end-to-end with neural networks and that there is really nothing else. None of us here were willing to take that kind of view. We're all much more pragmatist than that. And I think in this room, there was more, you know, there's not that many people who would make that argument. But I think, you know, there are people in different communities. If you go to NeurIPS, you go to ICML, you go to CVPR, you're going to see different opinions. And I think it's really important that that's a very important role for AAAI to remember that there are definitely many different modes of intelligence, definitely many different techniques for trying to study intelligence, and they can't be done in isolation. If we really want to achieve sort of a general theory of intelligence, it's going to require putting the pieces together and really valuing the work that it takes to integrate, which is not at all trivial.
Let's move to our next question from the audience.
So, as a machine learning researcher, I also agree that we need to explore this further and try to understand its limitations, its strengths, develop better algorithms. However, earlier we were talking about developing a general theory of intelligence. And I think the thing that if we focus exclusively on learning, especially like end-to-end systems as they are popular, we ignore the idea of priors and inductive biases given to the human mind that allow us to generalize in ways that current machine learning approaches cannot. I study continual learning, and neural nets suffer catastrophic forgetting. And we also see things in domains like natural language processing where we don't see the gains that we get as strongly as in computer vision or speech. Why is that? Well, we're starting to see some integration of, oh, we should look to linguistics. We should take some prior knowledge and perhaps incorporate into the structure reasonable ideas, or combining ideas like, why can't our neural nets reason? So perhaps we need to be thinking, the focus should perhaps maybe be tailored towards the hybrid, to integrating things, looking to cognitive architectures. And I think maybe that the way to tweak the statement is saying focusing only exclusively on the learning procedure by which we adapt the synaptic connections between neural processing elements, but instead looking to structures and trying to reverse engineer what evolutionary optimization gave us. I mean, we could try to evolve things and hope that artificial evolutionary optimization will yield the human mind, but otherwise, in the meantime, we're trying to extract those inductive biases ourselves and incorporate them. So I think maybe the focus needs to be still strongly on the hybrid or the intersection of the two, rather than exclusively on machine learning or the learning procedure.
I think in the interest of time, I'm going to encourage us just to hear from the audience unless they ask a specific question, because I really like to hear more than just a couple of comments. So let's just go back and forth, and let's limit ourselves to the people who are standing up now.
So my question is mainly directed at Peter's line of argument. So if you agree that a general theory of intelligence is going to require a large number of techniques, but we are focusing the majority of our efforts on just one of those techniques because we have a lot of momentum going towards it, isn't there a risk that then we are losing the ability? All of our effort is going into training people to do new AI researchers to do that one area, and we are going to lose the ability as a field to have a deep understanding of the other areas, making it difficult down the road to actually do the integration we know we're going to need to do.
So I do want to respond to that, because yeah, I want to invoke what Oren said at the beginning, that the views expressed here are not necessarily my own. That was the case during the debate. I did take a much more extreme position. I think to re-emphasize your point, I think yes, I think it's very important that we teach today's generation of students the history of artificial intelligence, the broad set of techniques, and it actually really bothers me. I've seen some of the folks who do argue that neural networks are everything now. I've seen an argument multiple times where it starts by saying, isn't it great that we kept alive this small community of neural network researchers when the rest of the community was doing other things? That's what we need. Diversity was great. Now, because of that, we can see that neural networks are working, and now nobody should do anything else. Right, a completely inconsistent argument that I think we need to resist, and for exactly the reason that you say.
I'd like to see the panel have some fun with the following. Gartner has the hype curve. How many people here know what the hype curve of Gartner is? Okay, so only a minority. Very briefly, the hype curve says people tend to overestimate early on in a technology area how quick its impact is going to be, then have their expectations dashed, and then in the longer term, for important technologies, it actually exceeds what they originally thought its impact was going to be. So every year, Gartner publishes a report, and they place different technologies where they are along this hype curve, which has a couple of inflection points. This year, guess what was at the top of the hype part of the hype curve? Deep learning. Yeah, the second time, that's right. Deep learning. So I'd love to see your responses, panel, at least one of the panelists, to that. Seems like you could make some hay with that, as your real opinion or as your mock opinion.
Nobody seems to be biting, and we're really short on time, and I don't want to cut off the other audience questions. So let's try to go quickly back and forth.
Sure. So let's not talk about research. Let's talk about education. What I've seen over the past 5 years is more and more introductory AI courses that are so dominated by machine learning, even before the deep learning craze, that there's no time left for classic approaches. And so I've seen a whole generation of AI researchers being trained. They get out and they claim they're an AI person, and they've never actually been exposed to many of the classic ideas. Does anyone on the panel believe that's a good idea? Or does anyone think that it's okay to have so much of a culture of evolution that we just lose all the stuff that we knew?
Absolutely not. Horrible idea.
And what can we do about it? Later.
I've never before seen a moderator ask the audience to make statements instead of questions and have that not work. Usually it's the other way around.
Yeah, statement, not a question. I'd like to just add to what Oren said about the quick next paper publishing machine. I'd just like to, and this is addressed to the younger people in the audience because any of the older people won't change anyway. And I wrote it out here. When I was a grad student ages ago, my thesis advisor, Herb Simon, said to me, if you see a research area in which a lot of people are working, go somewhere else to work.
Thanks.
I'd just like to say amen. Thank you for that.
My question to Dr. Oren, who made a really fantastic case against the merits of the proposal, is why don't you consider instead the inevitability of the proposal? Like, we know, all of us agree that getting the paper accepted is the important thing. So if you think about that, that's a classification problem, and just a binary one. So like, even if all of us machine learning researchers can't make artificial general intelligence, surely we can make an AI for paper acceptance, and one day the gradients will lead us to a place where the matrices reject every non-ML paper.
Who exactly do you think has been reviewing all these submissions with really lousy, barely coherent reviews?
Hi, so my comment is regarding the bias in models that was mentioned. So we all agree that AI for social good is deeply needed, and I would say that a layer of ethics before and after every model that we can reason about, like with rules. So logic is deeply needed for society.
So,
Not now. No. Oh, I'm sorry, go ahead.
Statement, I guess, right? First, I was surprised no one made the argument not what ML can do for AI, but what AI can do for ML, right? To me, there's actually a lot of reason to think about this community doing it, although this is not my community, so I can't tell you what to do. But one of the comments that came up at the end, this whole question of open world and being able to recognize you don't know something, recognizing I need to learn that, figuring out how to do that, right? No current neural network is going to solve that problem. You need a higher level control process to figure out what to learn, when to learn, how to learn, right? It's not just a functional approximation problem, and that problem isn't going to be solved by just throwing a deep network at it.
So I just want to all of these comments, I think these are great comments. I want to react briefly just to the hype comment from Ben and also to Ed's comment about not jumping on the bandwagon. With regards, and this is partly also to the younger people in the audience and just to our community, what we've learned from the hype cycle is the higher the hype goes, the bigger the disappointment gap, and then the bigger the crash is afterwards. I think we do need to work very hard as a community to keep the hype from going too high, to try to keep things grounded and realistic. And several of the people on the stage here worked with me on the AI 100 study panel report, where this was one of the goals, is to try to make that case strongly. And then I think, you know, Ed's point that he said from Herb Simon, Herb actually said exactly the same thing to me, and it's one of the reasons that it's really shaped my career as well. I think in today's world, if you want to have an impact, you should not be following the bandwagon. You should be trying to keep alive these other areas in artificial intelligence. They will, just like neural networks is having its day, these other areas will have their day. And if you're one of the people who keeps them alive, you will have you'll benefit from that when the light comes back and shines on it, and you'll play a really much more impactful role in your research. So I'd like to encourage people to do that in really all sincerity.
Great, and with that, let me just wrap up. So first of all, let me again thank our panelists. Regarding the comment that was made at the beginning about the composition of the panel, putting a panel together like this is not easy because a lot of people are scared to come up and express extreme views in front of a giant room full of incredibly intelligent people such as yourselves.
I'm not.
A lot of people, mostly people, are scared. You know, there wasn't some Machiavellian master plan about exactly who to put on the panel. These are the brave people who were willing to come before you to put this on. I think, again, they deserve a round of applause.
I really just want to highlight actually Kevin's role, because sure, we had to go and express ourselves, but he had the most stressful job, right? He had to take this on. You don't know how many emails and arms twisting and so on he had to do to put this together, and then he had to kind of keep us all more or less together. So Kevin, really a great contribution. Thank you.
And I guess to conclude, I just wanted to make one really brief personal remark, which is that I'm just really heartened by I had no idea how this was going to be received, how you would all vote, but it really makes me see, you know, why I like this community so much. Just the respect for diversity of views, diversity of intellectual approaches is just, I think, something really wonderful about this community. I'm really pleased by everything we heard from the panel and from all of you. So enjoy the rest of the evening. Thanks.